rectangular coordinate system and vectors in space. What does space mean besides outer space? From now on, it's going to mean 3D. So when somebody says, the curve is in space, that means it's a 3D curve, as opposed to a curve in the plane. What does the word plane mean?
2D.
2D, good.
2D.
So let's take a look at a picture of a 3D rectangular coordinate system right here. So you'll notice that you've got an x-axis pointed kind of to the left somewhat. You've got this y-axis pointed here to the right. It looks like it's kind of coming off the page. And the z-axis is pointed vertically up. And in this class, and it's in our textbook too, these are the positions of the coordinate axes. If you're taking a physics class, they have it all finagled in all different ways. I think I've seen physics where they go like X, Y, and like Z is this way or something like that. When I will be asking you to sketch some things in your quizzes and exams on your paper. And so you need to follow the convention we're using in this course. All right, otherwise no credit. I want to see the physics version of the coordinate axes. All right, back when you took your 2D stuff, we knew that there were 4 quadrants and we even know where they were located. But in 3D, you have 8 octants, 8 locations. You don't have to memorize all 8. I don't even know where they all are. But octant 1, I do want you to know. You remember quadrant 1 is where both X and Y are positive in this region. In octant 1, which is kind of coming out of the page here, it's right here. It's where your X, Y, and Z coordinates are all positive. That's the first octant. Great. What else? Well, a couple other things while we're here. You'll notice that in this picture, they've got sort of this blue flat plane here. That is called the XY plane, and it's flat, and it contains the X and Y axes. And when you're in the XY plane, the Z coordinate is understood to be 0. Another one of these coordinate planes that you need to know is this one here. It's got the X and Z axes in it. And it's understood when you're in the XZ plane that Y is automatically zeroed out. And finally, the third coordinate plane is this one here. And that's the X or the YZ plane. And it's understood that X is zeroed out in that coordinate plane. So know the 3 coordinate planes, and that way you can be clear as the class progresses and you know where things are. And it'll be easier for you also when we get into really having to visualize a lot of surfaces in 3D. Okay. To denote a point in 3D, you use an ordered triple instead of an ordered pair. You guys remember ordered pairs look like parentheses X comma Y. Ordered triples look like parentheses X comma Y comma Z. And they're showing you how to plot a point in 3D there. If it's 3, 4, 5, go 3 units along the X-axis, 4 units parallel to the Y, and then 5 units parallel to the Z, and you can locate your 3, 4, 5. Yeah. Let's look at some formulas in 3D. So we're going to look at 3 formulas here. The X or the distance, midpoint, and standard equation for a sphere. The distance formula in 3D is super similar to the distance formula in 2D. So let me just remind you of what that looked like. If you had a point P in 2D and a point Q in 2D, and the coordinates, say for P were X1, Y1, for q, x2, y2. The shortest distance between those 2 points, call it d, was the square root of the sum of the squares of the differences of the coordinates. You probably remember that from algebra. When we extend that to space, so if you have coordinates p, x1, y1, z1, q has coordinates x2, y2, z2, the distance between those 2 points, square root of the sum of the squares of the differences of the coordinates. Midpoint formula. Well, what's the midpoint if you're in 2D? Well, the midpoint between 2 points is just the halfway point. Call it M for midpoint. And in 2D, to find midpoint coordinates, you just take averages of x and averages of y. So you add the 2 x coordinates together, divide by 2. That's essentially the average of those x coordinates. And then the y coordinate is simply the average of the y's. And the midpoint is found similarly in 3D. Except it's going to be in order triple. So x1 plus x2 over 2 is the x coordinate. y1 plus y2 over 2 is the y coordinate. And z1 plus z2 over 2 is the z coordinate. Be careful because sometimes when students are trying to memorize a lot of formulas for themselves, in the distance formula here, you'll notice there's minus signs in between the coordinates, right? But in the midpoint formula here, you're taking averages of coordinates. So you've got plus signs here, not minus signs. I've seen students accidentally reverse those, and that's a silly mistake that you like to avoid, especially on a quiz or an exam. But look, I know silly stuff happens on quizzes and exams. We're all guilty of it. Students are in a fragile state when they're taking exams. I get it. What about the standard equation for a sphere? Well, let's do a circle first. That's the analog in 2D. When you did circles back in algebra class, your circle had some center point with coordinates a, b, and it had some radius r. And the standard equation for a circle looked like this. It was x minus the center point's x coordinate a squared plus the quantity y minus b squared equals radius squared. You may remember that from the bad old days. What about a sphere? Well, a sphere is a surface, and in 3D, here's 3D, a sphere looks like a ball, and it's just the boundary of the ball. So here it is, here's a sphere, okay? And you've got some center point here, I'll call it with coordinates A, B, C, and let's say you were told it had some radius r. Then the standard equation is the quantity x minus a squared plus the quantity y minus b squared plus the quantity z minus c squared, and that equals the radius squared. So it almost looks like a circle. You just extend it. So we're going to do a couple of sphere examples. The first one, we're being asked to find the center point and the radius for a sphere with this horrible looking equation. Oh my goodness, that is awful. Yuck. We're going to work on that and try to get it to look like standard form because we like standard form. This is good. Why? Because you can look at it and easily cherry pick the coordinates of your center point right off of the equation, and you can cherry pick the radius squared, and then that helps you get your radius very easily. But if it's in this big mess, there's no hope. So let's use a hint. We're going to complete the square 3 times in order to write the equation in standard form. Yep. Well, how are we going to do that? Very carefully. And yeah, you're going to have some problems like this on your homework and stuff. Oh, yeah. So what I do to help me make it easy is I put the x terms next to each other and leave some space. Then I put the y terms next to each other and leave some space. Then I put the z terms next to each other and leave some space. And then the constant term, 19, I subtract it from both sides and move it to the other side of the equation. That's my starting point. Okay. So now what? You're gonna add a magical mystery number M1 to make this a perfect square trinomial. And then it'll be factorable. And then you're going to find another magical mystery number, call it M2, to make this a perfect square trinomial. And we'll find a third magical mystery number, M3, to make another perfect square trinomial. But you can't just add numbers to one side of an equation and have it be legal. We better add M1, M2, and M3 to the other side to make it all work out. So how do you get these magical mystery numbers? Well, if you remember from your complete the square days, it's always going to be the middle coefficient, b, divided by 2, the quantity squared. So for us, M1 is going to be 9. This is the middle coefficient over 2 squared, which is 81/4. I know, not pretty. M2 is going to be -2 over 2 squared, but that's just -1 squared, which is 1. And then M3 will be 10 over 2 squared, but that's 5 squared, which is 25. So now the middle or intermediate step here, let me just kind of cue things up. When I add the 3 magical mystery numbers to both sides of the equation, I'm going to have the equation now look like this. Don't forget to add all 3 of those numbers to the right-hand side also. So how does this factor? And I claim it does. It's going to always factor as x plus b over 2. You're guaranteed. So for us, that's x plus 9/2, the quantity squared. If you don't believe me, FOIL it out. A little bit plus signs here. Plus, what does this guy factor as?
Y minus 1 squared.
And then how about that last trinomial?
Z plus 5.
And now get out a calculator and add up all those wacky numbers on the right, and I get a weird fraction, 109/4. Okay, good news. We're halfway there. We have the sphere in standard form. Cherry pick the center point and radius off of this equation. I'm going to put the wrong answers here, so you play teacher and tell me, what did I do wrong?
You had to count for the signs. So it's supposed to be like -9/2.
Good. Yes, and the reason why is because if you look at standard form for a sphere, the center point coordinates are all sitting next to a minus. So if you have a plus, you might want to think about it, at least in your head, as being a minus minus, and there's your x coordinate. How about anything else in that center point need fixing?
We need to include the very like x,
Negative
y, and
5.
z.
Yeah, the
Negative
-5
5.
I heard somebody say. That's true. Anything else, or is the center point good now, or what?
Yeah, get the square root of 109/4.
Yeah, this needs fixing. This should be the square root of 109/4. And I'd like you to go one more step for this particular problem, just because square root of 4 happens to be nice. Otherwise, you could have just left it. And so the radius is this strange number, square root of 109/2. And your center point is -9/2, comma 1, comma -5. And we're done. Okay. So Anything else for this problem? I think we're done. Let's do another sphere problem that's really classic. Most likely it'll be on a quiz or an exam. That's a big hint. What I love about this example 11 is it involves all three of the formulas on the last page. So let's take a look at how that works. They're giving us 2 points that live on the boundary of the sphere that create a diameter. And so what does that mean? Well, if here's 3D, like so, and you've got some sphere here. Let's say this point over here is the 5, -2, 3, and then we're creating a diameter here. So way over on the other side is this 0.04, -3, like so, right? And this is not drawn with actual points. I'm just trying to be very quick here. So I hope you recall from your old geometry days that radius is always equal to half the diameter, right? So that's an important point that we need to keep track of. And the center of the sphere is going to be located as the midpoint of those 2 points. So that's where the midpoint formula is going to come in handy. Yeah. And then of course we're going to need the sphere equation once we get our radius and center point all squared away. Okay. So there's different ways to approach this problem and it'll still work out as long as you do everything legitimately mathematically wise. So I'm going to do it just the way my personal preference. I'm going to first find the diameter length by using the distance formula between those 2 boundary points. And then to find the radius, I'll take half. And then I'll use the midpoint formula to get my center point. And then I'll have all of my ingredients that I need to plug into the sphere formula. And I'm going to do it in that order. Okay. There is an alternate way to do it, but it involves more fractions, and I try to limit my involvement with fractions. Okay, so the diameter, which is the same as the distance between these 2 points, is going to be the square root, big old square root, of the difference of the x coordinates squared. That's a 0 there. Plus, so 5 minus 0 squared, plus the quantity -2 minus 4 squared, plus the quantity 3 minus a minus 3 squared. Uh-oh, there's a lot of minuses running around. That means there's an opportunity for silly mistakes. Let's hope we don't make any. Yikes. Square root of 5 squared plus -6 squared plus 3 minus a minus 3 is really 3 plus 3. And don't forget, when you square a negative, it's the same as squaring the positive. And then what the heck is 25 plus 36 plus 36? So my diameter is square root of 97. So my radius is going to be half that. So save this for later. And then the center point is the midpoint of those 2 boundary points. So remember, to find center points, you basically take averages. You take the average of the x coordinates, add them up, divide by 2. You take the average of the y coordinates, add them up and divide by 2. And you take the average of the x coordinates, add them up and divide by 2. And then reduce these to lowest terms if it reduces. Let's see here. I think we can clean this up a little bit. Well, the first term here, I'm going to leave it. How about 2 over 2? Doesn't that reduce? How about 0 over 2?
Is 0.
And there's your center. We're almost done. So now I just need to come up with the standard form for the sphere equation. So of course I didn't leave myself any room to get my final answer. Why, oh why do I do that to myself? I don't know. I'll put it way up here at the top. So I'm going to go x minus 5/2 squared plus y minus 1, the quantity squared, plus z minus 0 squared, but that's just z squared. And then when I take my radius, square root of 97 over 2, and then square that quotient, I can clean that up a little bit. And I'd like you to if you want full credit. So when you square square root of 97 halves, I get 97 fourths. Because it doesn't look pretty when you leave that radical squared in your answer. It looks kind of unfinished. There's my final answer. Let's do some forms and facts for vectors in space. The component form for a vector in space, that's 3D, looks almost the same as the component form for a 2D vector. It's just got an extra component there. Yep. What about the linear combination version? Oh yeah, we're still going to have that. So when you do the linear combination, you have to take into account we have a third standard unit vector. What do you mean? We've got one called K. And also the I and J get changed up just a little bit because they're now embedded in the 3D coordinate system. So that means they have 3 components instead of 2. So the I is 1, 0, 0. The J is 0, 1, 0. And the K is pointing in the positive Z-axis direction, and it's got component 0, 0, 1. So you got the IJK standard unit vectors. And what does that mean? That means that any vector in 3D can be written as a linear combo of IJK. And of course, I love to show you a meme on that. Let's see if I can pull it up.
Do we need to like memorize all these unit vectors?
Yeah.
Okay, that's what I figured.
Good news, though, we're done. We're not going to do 4 dimensions or 5 dimensions or 17 dimensions. So IJK is the most you need to memorize. Does that help?
Yep.
So let's say you're given 2 points in 3D. So let's say the initial point was P with coordinates x1, y1, z1. And let's say your terminal point was called Q with coordinates x2, y2, z2. If you were trying to form the vector PQ, and remember order matters, you'll go terminal minus initial, terminal minus initial, terminal minus initial. Equality of vectors. We did this earlier this week. If you've got 2 vectors and somebody says they're equal, then you can be assured that you're safe when you can say that their components all must have to match them. They have to. Guaranteed. Okay, vector addition. Similar to 2D, if you're being asked to add 2 3-dimensional vectors with each other, you'll get a resultant vector. X component is just the sum of the X components of the original vectors, U1 plus V1, comma, U2 plus V2, comma, U3 plus V3. Boom, we're done. How about unit vectors? Sure. You can unitize a 3D vector. Use the same formula as unitizing a 2D vector. You take your vector and you simply divide it by its magnitude. And so your answer would look like V1 over magnitude of V, comma V2 over magnitude of V, comma V3 over magnitude of V. And that's a unitized vector, which means the magnitude is 1. Scalar multiplication in 3D, it's similar to as in 2D. You do want to distribute your scalar over your components. And scalar multiplication just means that you're stretching or shrinking your vector. That's what scalar multiplication does to it. There's the picture of the IJK again. Let's do example 12, which will put all of the previous topics together and hopefully bring some clarity. So let's say you're given an initial point A with coordinates -2, 3, 1. and a terminal point B with coordinates 0, -4, 4. Let's get the following. Give me a vector AB. Okay. So let's put it in component form because they're asking us to. You're going to go terminal minus initial, 0 minus a -2, comma, terminal minus initial. So -4 minus 3. Order matters. Terminal minus initial, 4 minus 1. Do the arithmetic, clean it up. So the component form has scalar components of 2, -7, and 3. And we're done. There's the answer to letter A. Well, how would you write that same vector as a linear combo of those 3 standard unit vectors in space? No problem. Just use your I, J, and K now, but no angular brackets, because this format doesn't require brackets or commas. You're going to go 2I hat minus 7J hat plus 3K hat, and you're done. Okay, letter C, they want that. What the heck is that? What does those double bars mean? Anybody remember the notation?
Magnitude?
Yeah. Magnitude. Okay. So good news, it's easy to get that magnitude when you already have the component form. You're just going to go the square root of the sum of the squares of the components. Yeah, but one of those should be a -7. You screwed up, teacher. Well, I usually get kind of loosey-goosey because when you square a negative, it gives the same result as a positive. So I don't even bother. I'll let you do that also on your exam for that particular case anyway. Okay, what's 4 plus 49 plus 9? Square root of 62, and there's the exact answer. Don't give me the decimal result. When they ask for exact, they mean it. Same with my lab math. Like if you accidentally whip out a calculator now, figure out the decimal and type it into my lab math, when they ask for an exact answer, they're going to give you 0 points. I'll probably just take off 1 or 2 for not following directions. So I'll give you some of your points back. Okay, D and E have to do with unit vectors. A unit vector pointing in the same direction as V is going to be the vector divided by the scalar, which is the square root of 62. MyLab Math will give you full credit if you type it in like this. I won't. I'll take away points. Well, how come? Because I like it where you actually do one extra step for me. Distribute the scalar, please. I don't require you to rationalize denominators, so don't bother doing that. This is totally okay with me as the final answer. And you unitized. We unitized it, which means the magnitude of this result is what? What's the magnitude of a unit vector?
1.
Good, 1. And then letter E is easy because they just want a unit vector pointing in the opposite direction of V. So how can we get that?
Take a negative.
Multiply by -1.
Yeah, just flip the signs.
Yeah, flip the signs. Perfect. So I'll just flip all the signs from my answer from letter D and I get it right. Perfect. And I'm done. And we're done with this example. Let's define what parallel vectors are, and we'll do an example, and then we'll do a little bit of wrap up for section 13.2. We're almost done. So what are parallel vectors? I'll show you visually what they look like, and then we'll do this definition. So if you were to look at a vector, say U, let's say pointing that way, a vector that's parallel to that guy would be a vector pointing in the same direction, or a vector pointing in the opposite direction. All 3 of those vectors are parallel with each other. Okay, but I'm not going to ask you to always be sketching and drawing all these vectors in order to distinguish if vectors are parallel or not. That's going to be tough, especially if you're as bad as an artist as I am. Might kind of look like they're parallel, but they're really not. Okay, so the official way to do it is if they're non-zero, because remember, zero vector, this looks like a dot. Non-zero vectors, you want them to be healthy and looking good. They're parallel if there exists some scalar C such that one of the vectors can be written as a scalar multiple of the other vector. And that's how you know if you've got parallel vectors or not. So this example, we're given a vector W, okay, and we're going to determine if the following vectors are parallel to W or not. If yes, figure out the scalar C such that V, the vector given, is a scalar multiple of the W. Okay. So is V a scalar multiple, we'll just put the C here, of the W vector? And let's distribute the C, so we'll have negative 6C, 8C, 2C. And now if these vectors are going to be equal, you're going to equate the components. So we need 3 to equal negative 6C. At the same time, we need negative 4 to be equal to 8C, simultaneously, that is. And then we need the negative 1 to be equal to the 2C. Solve for C 3 times in a row, and all of the C's have to be a match, and then that will mean it's parallel. Otherwise, not parallel. So when I solve for C 3 times, and then of course you can reduce, do all of these C's look like they are equivalent?
Yeah,
Mhm. So does that mean we have a parallel vector on our hands?
yep.
Yep. Yes, parallel. And we're done with letter A. Great. What about letter B? Is that parallel to W? I don't know. Does he look like he's going to equal CW, which was negative 6C, 8C, 2C? And again, you'll equate components. And solve for C 3 times. And reduce. Do all of these C's look like they are equivalent?
No.
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 One of them is positive and the other 2 are negative. So no, not parallel. Because if even one of them is not equivalent, you're done. You don't have parallel vectors. It's not a bad thing. It's good to know if they're parallel or not. These 2 aren't. Okay, we're done talking about parallel for now. It'll come up again in the future, but now you know what the quick and dirty way to figure out if 2 vectors are parallel or not. If they're scalar multiples. Okay, new topic here. Check out this example. Write the vector, and this is easy peasy, 4i minus 5k in component form. Okay, so how do we do that? Component form means we use angular brackets. Anybody have an idea?
Do we just multiply it by 1, 0, and 0, 1 for the I and K?
Well, you could. That'll help. That would be an intermediate step. There's a quicker way. I think you can just do it by inspection.
Can you just do 4, negative 2? Right? Oh, no, never mind.
Is it 4, 0, negative 5?
4, comma 0, comma negative 5. And we're done.
And that's because we're missing the J, right? The J hat?
Correct.
Okay.
Because there is a K there, it's understood you're working with a 3D vector. So you have to put in a placeholder for the J. You can't go, well, he's gone, so forget him. Oh, no, that's not right. Don't forget about him. He's good. Okay, now I want to do a side note now that's not in your lecture notes. Earlier this week, I stated that I'm not a big fan of the IJ or the IJK format, even though it's going to be throughout the semester. You'll see on your quizzes, homework, everywhere. The physics folks, that's all they like. They don't like component form. They like all the I's and J's and K's. But here's why I don't. What if somebody told you, okay, here's a vector in space, W is equal to, I don't know, 2I hat plus 3J hat. And then I was going to put it in component form. This would be wrong. Well, how come? There's no K. But if you are working in 3D, you have to acknowledge the fact that there is a K, even if the K is not shown in your IJK format, if you're really being told that you're working in 3D. So the correct component form for this particular vector, since they're telling us, hey, you're working in space, 3D, has a 0, and it does have a third component. Now, on the other hand, if you were told this W is a 2D vector, and you were working in the plane, then of course your component form would only have 2 components, because you don't have a K when you're working in 2D, okay? So why, again, do I prefer component form? Because there's never any confusion about whether your vector is a 2D or a 3D vector. You immediately know just by looking at it. And it's not altogether apparent if you're looking at the IJK version, if the K is missing. And that's why I prefer component form, folks. All right, I'm done with the side note. Let's do example 15. This is a retro engineering backwards kind of problem. What do you mean retro? Well, the forwards type is like, here's an initial point P, here's a terminal point Q. If you form the vector PQ, the way you do it is you go terminal minus initial, terminal minus initial, terminal minus initial, boom, and you're fine. But here, the reason why you have to retro engineer it is even though they're giving you the initial points coordinates, -2, 3, 5, they're not giving you the Q terminal point. In fact, that's what they want you to give. They are giving you the V vector though, the PQ. I'm going to put it in component form, 7, -1, 3. So how do you get Q's coordinates? Because that's the problem. Find the terminal point. Well, the unknowns here are Q's coordinates. So Q, which is a point, that's why we use the parentheses here, not brackets, because it's a point, not a vector. If you're going to retro engineer this, you would want terminal point minus initial point X coordinates, oops, to be equal to the vector's X component. And then you could just solve this for X by subtracting 2 from both sides. And voila, you have Q's X coordinate. And similarly, you do the same for the Y's. Y minus 3 had better be equal to the vector's Y component of -1. And when you add 3 to both sides, you get 2. And then do Z minus 5 has to equal the Z component for the vector, add 5 to both sides, and then your final answer, when you put it into a point format, this is your Q, this is your terminal point.
On an exam, do we have to show that, or can we just add 7 to -2, -1 to 3, and then 3 to 5?
I want you to show the intermediate steps.
Okay.
Please. A good rule of thumb for how much work that I like you to show me on a quiz or the exams, your handwritten work. Let's say you had a cousin down in Grossmont College and they're a little bit more of a, let's just say a slower style of learning. And they were looking at your quiz or exam homework or whatever your written work is, and they were trying to figure out what you're doing. And if they're going to be confused, like, ooh, I don't know what you're doing, I still don't get it, then that means your work is not in alignment with, you know, kind of showing me the steps in a brutally honest manner, basically. Don't skip steps. Too many steps. Okay. I mean, within reason, like, you know, if you're solving like a baby elementary algebra equation and, you know, in a beginning algebra person would show me every bloody step, it'd be, you know, you don't have to maybe go drill down that far. But within reason, I want to be able to understand what you're doing. Also, too, speaking of, you know, people going on websites to get answers, a lot of these websites show answers, and a lot of times they skip steps. And I kind of know, I can tell, because I go to those websites too to see when somebody's not really doing their own work. And when I see, oh, the website skipped a whole bunch of steps, and then that person did too, it makes me suspicious. Okay, we're going to wrap this up. By the way, I'm going to go past 11:30 today because we took about 15 minutes to square away some of your questions and so on. So if you have to leave early, I get it. Watch the video. I have office hours at noon today. You're all welcome for 2 hours. It's a party. Come on down. 3 forces act on an object. 2 of the forces are at an angle of 100 degrees to each other and have magnitudes 25 newtons and 12 newtons. Ooh, newtons. You're using the metric system. Oftentimes you're using newtons instead of pounds. In the previous couple examples we did, the units were pounds, but here they're newtons. Different. The third force is perpendicular to the plane of these 2 forces and has magnitude 4 newtons. Calculate the magnitude of the force needed to counterbalance all 3 of these forces. Oh my goodness, what the heck? This seems really hard. Well, first up, this is a 3D problem, but let me just start in 2D because it sounds like these 2 forces initially they're talking about, they're in the same plane. So let's just assume they're in the XY plane. I mean, they may be in a different plane, it doesn't matter. The first force, let's just pretend that he's sitting on the x-axis. Well, what if he's not? Hey, we get to decide. And they said he's 25 newtons, so the 25 mark. We'll call this F1. 100 degrees to that is the other guy who's not as long because he's only 12 newtons. So there's F2. Okay, now the third guy is perpendicular to the page, to this plane. So the third guy is like sticking straight up out of the page. So if I'm now going to try to draw this same picture using the 3D rectangular coordinate system, here I go. F1 is sitting on top of the positive x-axis. Remember, there he is. In this XY plane, but 100 degrees over, is F2. He's a little shorter. And then F3 is perpendicular to both of these guys. He's making a 90-degree angle with both. So see, he's sticking straight up, and I will call him F3, and he's only 4 units tall, or 4 newtons. Okay, and the question is, that if we did get the resultant vector's force, and we wanted a force to basically obliterate that resultant force, how would we do it? So here, I'm going to tell you my strategy in 3 steps, and then we'll do the 3 steps in order. Step 1, get the component form for all 3 forces. Step 2, get the resultant vector. What's that? Well, we're going to go F1 plus F2 plus F3. And we'll get a big old vector, big one. Step 3, get the magnitude of that big old resultant vector. And that will be the answer. Here's my strategy. I'm sticking to it. And I didn't leave myself enough room. I'm gonna append a page. Okay, so how do you get the component form for all three vectors? We are in 3D, so we are going to need three components. Now F1, since he's sitting on top of the x-axis, he's going to have 25, 0, 0 as his components. That should be clear. He's sitting on top of the x-axis. Now F2, because he's kind of swinging out 100 degrees, we can use that idea of magnitude times cos of the angle he's making with the positive x-axis, comma, 12 times 12 is his magnitude sine of that angle he's making. And because he is in the xy coordinate plane, it's understood that his z component is zeroed out. You can get that for free. And finally, F3 is sitting right on top of the z-axis. He's parallel to the z-axis. So it's understood his x and y coordinates, or components rather, are zeroed out, and he'll just get that 4, because that's how his length is pointing in the z-axis direction. So now we have everybody in component form. Yay for us. Now what? Let's add all three of these vectors together to get the resultant vector. F1 plus F2 plus F3, gonna give me a big vector. Add all the x components together to get the resultant vector's x component. Add all three y components together, and we get the y component, and then add all the z components together, and then finally go and get the magnitude of this big old resultant vector. And that's when you want to whip out the calculator. And you got to use parentheses in a lot of different places. I know it's kind of a hassle. Make sure you're in degrees mode for this one. And I get 26.092. Couple things we need to do this answer to get full credit. One, we need to round to the nearest tenth. Does anybody know how many decimal places tenths are? Round to tenths.
It's just one, isn't it?
Good, one decimal place only. Very good. So if I were to round this to one decimal place, I get 26 point what?
1.
And then I need units. Are my units pounds, miles, meters, square inches?
Newtons, right?
Newtons, good. Big N, short for newtons. And I'm done with this problem. Yay! So the resultant force is 26.1 Newton force. And we're done with 13.2. Congratulations, everybody. You now know vectors in space. How do you feel?
Okay, I have a question for you.
Sure.
Okay, so I just want to slow down real quick. When you did the component form, I'm still having a hard time visualizing the third dimension.
Okay, that's fair. So the F3, are you having a little problems with?
Well, the F1, I know where the 25,0 comes from, obviously, because that's just on the, you could just interpret it as the XY plane. But are we interpreting that, like, if it's horizontal, that the K plane or K hat, or whatever you want to call it, that's also height?
Well, let's read what the word problem says, and that might square away some of your confusion. Do you see that they say, well, the first two forces are in the same plane, and the third force is perpendicular to the plane of the two original forces. So that automatically tells us that he's sort of sticking straight up. He could be sticking straight down too, to be honest. And we could have had his components be 0, 0, -4, but I kind of took a liberty here and went ahead and said he's got the magnitude of 4 newtons. And since he is perpendicular, that allows me to assume he is parallel to the z-axis. And that allows me to say that his x and y components are 0. And in order for him to still have a magnitude of 4 and yet have the two first components be zeroed out, this z component has to be a 4. Because the magnitude would be this. And so it works out.
Okay, that helps. It's
That's
just,
still confusing to you? May I suggest you come visit me in office hours and
it's
we'll
just gonna take some time to get
bring
used
this
to.
out? Sure. Mhm.
Okay, envision this. Imagine the z-axis as up and down, x as
Section 13.3, we're going to learn about the dot product. Then we're going to look at something projections and work. We'll do this next week. Next time. We are going to look at what a dot product is and one application of it today, and then we'll be done for the day. So what have we learned so far? Quick recap. We learned vector addition, adding a couple vectors together. Fine. So quick little pop quiz. When you add two vectors together, do you get a result that's a scalar or a vector? Which one?
Vector.
Good, a vector. Yeah, a vector plus a vector, it's a vector. Okay, good. What about scalar multiplication? When you multiply a vector with a pure real number like 2, do you get a result that is a scalar or a vector?
Scalar.
So like 2v, is that result a scalar or a vector?
The vector.
It's a
Scalar,
vector.
a vector, right?
So both of these answers right now are vectors. Okay, we're done with the review. Let's move on. The definition of dot product. Dot product is also known as the inner product. If you take a linear algebra class, they typically call dot products inner products. They're more fancy there. So let's do the 2D and the 3D version for a dot product. If you are taking a dot product of a couple of vectors in the plane in 2D, then you are going to use a little dot to denote the dot product. Surprise, surprise, surprise. And the answer will be the product of the x components plus the product of the y components. And the answer is a real number. You're going to get a pure real number as an answer, not a vector. In 3D, similarly, you are going to see a little dot. That means go get the dot product of those two guys. And the answer will be U1 times V1 plus U2 times V2 plus U3 times V3. Fill in the blank. And it's a real number. So now let's finish this sentence. The result of a dot product is here are your choices, scalar or vector.
Scalar.
Scalar is correct. It's your number. So now let's do some properties of a dot product. I'll do a couple of proofs and then we'll do some examples, okay? So let's say you were given u, v, and w and their vectors in the plane or space, doesn't matter. These are all still true regardless. And let C be some scalar. If you take the dot product of u and v, u dot v, it gives you the same answer as v dot u. So dot product is commutative. If you take the dot product of u with the sum of two vectors, you can either do it just like that. That's fine, nothing wrong. First do the v plus w, then do the dot product. But if you want to, it's legit to distribute u dot v plus u dot w. If you have a scalar c and you're multiplying a scalar with a dot product, you can either do it just like you see it there. First do what's inside the parentheses and then multiply the scalar. Or if you prefer, do the scalar with u, then take the dot product with v. Or if you want to do u dot product, that's a dot there, cv. These are all three equivalent. Which one's better? They're all the same. Do whichever one's your favorite. You should get the same answer. If you take a dot product of any vector with the 0 vector, it's what you'd expect. You'll get 0. I put a couple stars next to the last guy because he is interesting, and this will come up later. If you take the dot product of a vector with itself, it'll give you the same answer as its magnitude squared. Interesting. So I'm going to prove number 1 right here. Let's look at u dot v. You'll get u1 v1 plus u2 v2 plus u3 v3. Fine. Now, by the commutativity of real numbers, because real numbers are guaranteed to be commutative, this is equivalent to v1 u1 plus v2 u2 plus v3 u3. But that's just the same as v dot product with u, and we're done. I just proved that u dot v gives you the same answer as v dot u. Not very interesting, but that's the proof. How do I prove number 5? Oh, carefully. Let's do v dot product with itself first. Let's just do that left-hand side. So you're going to get v1 times v1 plus v2 times v2 plus v3 times v3. But using the fact that repeated multiplication can use exponents, you really have v1 squared plus v2 squared plus v3 squared. Stop there and save this for later. Let's look at the right-hand side of the formula. What does the magnitude of v getting squared look like? Well, magnitude involves a radical, and then you're going to square it. So you're going to have the radical is the sum of the squares of the components. That's how you take a magnitude. But anytime you square a square root, the square root goes away. Would you agree that these are equal?
Yes.
I'm done. I just proved what I needed to prove. Check. This is definitely true. Yay! And we're done. Okay, now let's have some fun and play with dot product and some of the stuff you've learned in the past, like scalar multiplication and stuff. So here are 3 vectors, and they happen to be 2-dimensional vectors. That's fine. And we can tell just by looking at them because they have the 2 components. So let's do letter A, easy peasy. What is u dot v? Well, the dot product is easy to find. You just take the product of the x components plus the product of the y components, and I get 10 plus negative 16, which is negative 6. And I'm done. And that's the answer to letter A. And notice the answer is indeed a scalar. Letter B is a little tricky. You're taking the dot product of u with v, and then once you get done with that, you're going to multiply it with w, which is scalar multiplication. Now, I already did u dot v, so I don't feel like doing it all over again, if you don't mind. So really what they're asking us to do here is take that dot product, which we got was negative 6, and multiply it with w. This is called scalar multiplication, which we learned already. And scalar multiplication is not a dot product. It's something else. You're going to distribute your scalar multiple, and I get the vector 24, negative 18. Well, I thought you said dot product gives a scalar. I did. But this involved the scalar dot product multiplying with a vector, and that's called scalar multiplication. That gives a vector result. Letter C, you're going to take the dot product of u with twice v. So I'm going to do this in slow motion. So u is 2, negative 2. And you're going to dot product that with twice the vector v, which is components 5, 8. So we're going to do the scalar multiple first. So we'll still have this 2, negative 2 waiting to dot product with this scalar multiple, which ends up being the vector 10, 16. And now we're ready to go do the dot product. Aha. So we'll multiply the x components, 2 times 10, plus we'll multiply the y components, -2 times 16, I get 20, plus -32, and I get a final answer of -12. Ta-da! And it is a scalar, because this was a dot product overall. And finally, the magnitude of W squared, which doesn't involve a dot product, but if you wanted to, it would give you the same result as W dot product with itself. Let's just use example 5 anyways, and I claim it'll be the same. It's just going to be -4 squared plus 3 squared, which is 16 plus 9, which is 25. And I'm done. And I'm done with example 1. And this is a scalar. So what is this dot product good for? A few things. It's very powerful. One application we're going to look at today, and then we'll look at more next time. Yeah, Lewis, I have the same problem. My U and V looks almost exactly the same, and I can't tell it apart. You'll have to work on it like me and make your V's have a very sharp vertex. What is the dot product good for? Okay, you can use it to find the angle between two vectors, which is really cool. So let's say you had a vector U and some other vector V out here somewhere. This angle between the two vectors, you can find it using this formula. Cosine of that angle theta is U dot V divided by the product of the magnitudes of U and V. Really? I don't have time to prove this, but you do need the law of cosines to prove it, which is kind of cool. It brings back some old trig memories from the bad old days, because you create a triangle here. This is the V minus U leg of the triangle. And then using this weird triangle, which is definitely not necessarily a right triangle, and you use the law of cosines and it all works out. And then you'll get this. Now, this formula is super helpful if you can figure out the dot product and the magnitudes, and then they're asking you for the angle between the two vectors. This angle I have here, please don't confuse it with a previous angle from a previous lecture where I was talking about 2D vectors and the angle that a vector makes with the positive x-axis, not to be confused with that theta, different. It's just the angle between two vectors, anywhere in space. And actually this formula works for 17-dimensional space or 100 dimensions. Okay, an alternate version of this formula, if you wanted to clear fractions and rewrite it, is this version of it. U dot V is equal to cos theta times the product of the magnitudes. Well, which version is good? Which one should I use? It depends on what they're asking for and what they're giving you. If they're asking you for the angle between two vectors, use this version, the first one. If they gave you the angle between the two vectors already and the magnitudes, you can use this alternate version to find the dot product. Instead of using the definition of dot product on our previous page, you can use this one. Pretty cool. Okay. Before we do a couple of examples and we wrap this up, I want to talk about this version. Dot product can be positive, negative, or zero. Dot product can be positive, negative, or zero. And how do you quickly tell if it's going to be positive, negative, or zero without even actually performing the dot product? Magnitudes are always positive. So they're not going to contribute to the positive, negative, or zero end result. But cosine can be positive, negative, or zero. That cosine is going to be the distinguishing factor on whether your dot product will be positive, negative, or zero. Aha. Mm-hmm. So I'm going to draw some real quick pictures here. Suppose you have a vector v and u is pointing exactly in the opposite direction. They're parallel, and you have a 180-degree angle between them. Okay, we'll work on that in a moment. And let's say you have v here again, but u is making an angle that's obtuse. So in other words, the angle is greater than 90, but less than 180. Another example would be, suppose the two vectors are making a right angle with each other, 90 degrees. What would happen? Two more little diagrams. What if your theta is acute? So in other words, it's greater than 0, but less than 90 degrees. And then finally, what if your vectors have an angle of 0 degrees between them because they're pointing in exactly the same direction? Cool. So quickly, just tell me what is going to happen with u dot v. Will it be positive, negative, or 0 for these 5 options? Well, here, cosine of 180 degrees, or cosine of pi, same thing. What does that equal? Anybody know off the top of their head?
-1.
Good. And since it's negative, that will automatically mean u dot v will be some negative number. Guaranteed, depending on whatever the magnitudes are, whatever the final result. Now here, if you have an obtuse angle, so in other words, an angle that's greater than 90, less than 180, does anybody remember what sign of cosine is when that happens? Positive, negative, 0?
I'm
Well,
sorry, what was the question again?
Is your cosine positive, negative, or 0 if the angle is greater than 90 but less than 180? Anybody remember from
Negative.
it would be
It's
negative.
negative. So that would mean automatically your dot product will be some weird negative number. Guaranteed. How about if your theta is 90 degrees? What's your cosine doing then?
0.
0. Very good. So if your cosine is 0, you're guaranteed that the dot product is 0. Put a big box around this diagram because that's going to come up in about 2 shakes. We're going to do a definition for that one. What if your angle is between 0 and 90? Is your cosine positive, negative, or 0?
It's positive.
That'll mean that your dot product will be positive too. Okay, finally, if your theta is 0, that means that they're pointing in the same direction. Cosine of 0, positive, negative, or 0?
It's going to be positive.
Because it's a 1, right? So that means your u dot v will be positive. I just want to show you this for all the different cases. So your dot product can be positive, negative, or 0, and it's based on what the cosine is doing here. Now let's define a very important definition for you. Orthogonal. Two vectors are considered orthogonal if u dot v is 0. In other words, cosine of the angle between them is 0, and that angle is 90 degrees, or pi halves, the radians. This is key. We're going to use it for the rest of the semester. The word orthogonal sometimes is used interchangeably with the word perpendicular, and they are the same, except if you go into multiple dimensions more than 3. So if you're in 4 dimensions, you can't really visualize what it means to be perpendicular anymore. That's why they use the more fancy word orthogonal. Impress your friends. Okay, last example of the day. Here we go. You got a whole bunch of vectors here. Oh my goodness. Find the angles between the pairs. Oh, I'm going to do this quickly because I already supplied the answers below. After you figure out the angle, answer this question. Orthogonal, that means 90 degrees. Parallel, that means 0 or 180 degrees, or neither. Here we go, u and v. Well, cosine of the angle between them will be the dot product of u and v divided by the product of the magnitudes of u and v. So let's see, I'm going to go 3 times -4 plus 0 plus 2 times 2 for the numerator. And that is all over square root of 3 squared plus 1 squared plus 2 squared times the square root of 4 squared plus 0 squared plus 2 squared. Oh dear, and this looks like, oh my goodness, -8 all over square root of 14 times square root of 20. And you can clean this up a little bit if you want, oops, although you don't have to. If you reduce this to lowest terms, I get -4 over square root of 70, but you don't have to. At this moment, what they're saying here is your cosine is this. That's not the final answer. You're going to need to take cos inverse of both sides and then go ahead and use your calculator. And I would be in degrees mode. It's easier. And I get approximately 118.6 degrees. So there's your answer for letter A. And this is neither orthogonal and it's not parallel either. So what about U and W? That pair of vectors, what do we got? Well, if I'm using my formula, I got to do the dot product in the numerator and I divide by the product of the magnitudes. Okay, fine. So U and W, 3 times 1 plus -1 times -1 plus 2 times -2. And then I'm not going to do the magnitudes. I'm going to leave them. You'll see why in 2 seconds. If you look at the numerator, what does that add up to? Are they still here?
Zero.
All right. Yeah. Now, what is 0 divided by a positive number?
0.
Yeah. And so what is that telling us? My cosine is 0. So cos inverse of 0 is 90 degrees or pi half. Orthogonal, parallel, or neither?
Orthogonal.
And finally, V and R, I'm just going to run through this fast. Cosine of the angle between them would be the dot product divided by the product of the magnitudes. And I'm going to get, and I'm going to do this really fast, I get -10 over square root of 100 after I do some simplifying. But that's -10 over 10, which is reducing to 1. Ooh, nice. So theta is equal to cos inverse of -1. And you don't believe me, this is 180 degrees or pi radians. And when this occurs, those vectors are parallel.